Hello and welcome to my next math video. This is for calculus and we're starting chapter 2. So here's an overview of the whole chapter. It's all about differentiation. 2.1 for this video will be the derivative and the tangent line problem. You might remember we talked about that way back at the beginning of the school year. And then 2.2, basic differentiation rules and rates of change. 2.3, we get into some higher rules, product and quotient rule, and derivatives for higher ordered function or higher powered derivatives. 2.4 is the chain rule. 2.5, implicit differentiation. Derivatives of inverses in 2.6, related rates in 2.7. That's a really fun section. And 2.8, Newton's method we will not do in this class. This class is specifically for the AP test, for the AB, calculus test, not the BC exam. If I recall correctly, Newton's method might be on the BC exam, but since this is an AB class, we're not going to spend any time on Newton's method. Before we get started here, real quick review here on this function notation. F of x is x squared plus x. Think of that x, in there just as a placeholder. Think of it as an empty set of parentheses. So here's x squared plus x. If I want to do f of x plus 3, I'm just going to change these x's into sets of parentheses. So this was x squared, now it's parenthesis squared. Plus, and then we had an x. I'm just going to put an open set of parentheses. And then we would put in the x plus 3. So now that it looks like this, it becomes a little more obvious what's going to happen. We're going to FOIL this out and get an x squared plus 6x plus 9. And here we kind of distribute the 1 and the parentheses disappear, plus x plus 3. And we could combine like terms. And then for something like this, again, our function is something squared plus that same something. Here, though, we're putting in a y squared. So that would be y squared squared plus y squared. So that would be y to the 4th plus y. So we're going to be doing a lot of this kind of stuff. We're going to be putting in something plus something else. And we might have to FOIL it out or even cube it to get to our answer. So here's 2.1, the derivative and the tangent line problem. Sounds easy enough, only 3 bullet points. Find the slope of a tangent line to a curve at a specific point. Use the limit definition to find the derivative of a function. And understand the relationship between continuity and differentiability. There is a one-way kind of relationship in there. That's, I think, the very last thing we talk about. So the tangent line problem. Calculus grew out of 4 major problems that European mathematicians were working on in the 17th century. The one we're going to talk about here, the tangent line problem. Velocity and acceleration, we'll see those in the next couple sections. Minimum and maximums on curves, we'll see that in 3.1. And the area problem, we'll see that in 4.2. Each of these problems does involve the notion of a limit, and calculus can be introduced with any of the 4 problems. A brief introduction to that tangent line problem we saw back in 1.1. Although partial solutions to this problem were given by Fermat back in 1600s, Descartes and Huygens, and Isaac Barrow. Credit for the first general solution is usually given to Isaac Newton and Leibniz, Gottfried Leibniz. Newton's work on this problem stemmed from his interest in optics and light refraction. So what does it mean to say a line is tangent to a curve at a point? For a circle, the tangent line at point P is the line that is perpendicular to the radius at that point. Think back to geometry. Here's our radius. A tangent line is going to be perpendicular at that point. And here, remember, a circle has a set curvature. But for a general curve, however, the problem is more difficult. For instance, how would you define the tangent line shown in figure 2.2? So here we got one like this. It looks horizontal. Here's the tangent line, but it's a little different than, the circle that only touches at one point. Same on this parabola. But here, our point of tangency, that tangent line would cut through the curve. And then here, in this last one, we see we're tangent at this point P. But if we extend the line, we are going to hit the curve again. So for general curves, it's not as simple as a circle because a circle has a set curvature. You might say that a line is tangent to a curve at point P when it touches but does not cross the curve at P. That would work for the first curve shown here, but not for the second, because we already showed that one. Let me pull it out here a little farther, that one right there. Or you could say that the line is tangent to a curve when the line touches or intersects the curve at exactly one point. This definition would work for a circle, but not for more general curves. Essentially, the problem of finding the tangent line at a point boils down to the problem of finding the slope of the tangent line at that point P. We can approximate this slope using a secant line through the point of tangency and a second point somewhere else on the curve. And this is how we did this back in section 1.1. Remember, for all the years you've had math, slope would be y2 minus y1 over x2 minus x1. The change in y over the change in x is your slope. Now let me see if I can get my line tool here. There it is. Oops. And if we set up, I'm just going to set up a first quadrant. So here is our first point. Let's call it, just call it x, I guess, x. And we hit a point, and that would be our f of x. Let's stick with the notation that we're going to be seeing here in a minute. Instead of x, as we did all our limit stuff, we were approaching a point C. So here's point C, and I'm just going to come up here a little bit, and this is where we're going to hit, and that will be f of C. So we want to find, it doesn't matter what the rest of the curve looks like. We want the exact slope at that point C, and we need another point. So let's move a little farther down the x-axis. I'm going to call this point C plus delta x, that little bit more. Greek letter delta, delta x, we have moved along our x-axis, and that will give me a point. I'm going to put it up here, and that would hit the y-axis at f of C plus delta x. So back to our old definition of slope up here in the corner in black ink, change in y over change in x. Let's just, update that with this new calculus stuff. So our y2 value would be this, the higher of the two in this case. So that would be f of C plus delta x. And then we subtract the first y value. That would be this f of C. F of C. And then we have down in our denominator x2 minus x1. Well, our x2 would be this one. C plus delta x. C plus delta x. And then we're going to subtract x sub 1. That is just C minus C. So right here in this denominator, we have a positive C and a negative C. They're always going to cancel out. So we're left with this. F of C plus delta x minus f of C over delta x. And remember, that delta x is just our movement along the x-axis. We did all that work on limits, so we can make this as small as possible. We're going to make it infinitely small. We're going to have those 2 points approach. So here, here's where the book did that. There's our old slope formula. We put in our different calculus notation, and we get this, m for slope, and there, that subscript secant, the slope of the secant line. This right-hand side here is called the difference quotient. Difference meaning subtraction. There is a subtraction between the two terms in the numerator. Quotient, it is in the form of a quotient or a fraction. The denominator delta x is our change in our x-axis, and our change in the numerator is change in y, so we could just write that as delta y. And then the book says the beauty of this procedure is we can obtain more and more accurate approximations of the slope of this tangent line by choosing points closer and closer to the point of tangency. So here we could delta x is approaching 0. So it's sort of, if we look at this triangle, that this base of it, the bottom of it, that delta x is shrinking. And as that shrinks, it's a right triangle. This other side shrinks. So it's getting smaller and smaller. It's getting pinched off right at that point. And that will be the slope of our tangent line. And the slope of the tangent line is the exact same slope occurring on that curve at that specific point. So here it is enshrined as a definition in the blue box. If f is defined on an open interval containing point C, and if the limit, this limit exists, the limit is delta x approaches 0, delta y over delta x, and remember instead of delta y, we're going to use that difference part of the difference quotient. So f of c plus delta x minus f of c all divided by delta x is our slope. So provided that that exists, then the line passing through that point with the slope m is the tangent line to the point to the point of the graph of function f at that point. The slope of the tangent line to the graph of function f at that point is also called the slope of the graph of f at x equals c. Now to take this for a test drive, we have a function, f of x is 2x minus 3, and they're giving us a set x value or c value. So here we're going to use this to find the slope occurring exactly at the point 2. So there we go. Since this is new to us, I'm just going to write the notation here, the limit as delta x goes to 0. So we're going to do f of, since they gave us this x value, that 2, let's just plug it in right now. That's going to be f of 2 plus delta x minus f of 2 over delta x. Okay, I always said when we encounter a limit, try direct substitution first. If we plug in 0 for delta x, our numerator is f of 2 minus f of 2. That will be 0. Our denominator, we plug the 0 right in. So we do get the indeterminate form 0 over 0. So let's put this into the function. I'm going to bring my limit notation down, delta x approaching 0. And I can put this delta x down here. So our function is 2x minus 3. So we're going to have a 2x minus 3 for this part. I'll underline in red. And I'll switch to black ink. And now it's minus f of 2. So this is minus, and notice I'm going to group this as we're subtracting it as a quantity. 2 something minus 3. So when we're using this difference quotient, you're going to use the function twice in the numerator. It's less confusing, I found, if we write it out like this with empty parenthesis. 2 times something minus 3 minus quantity 2 times something minus 3. Now in the first use of the function, we put in a 2 plus delta x. In the second use, we just put in the 2. And now we let algebra take its course. We're going to distribute. This 2 here will get distributed, so that'll be 4 plus 2 delta x. And then we have our minus 3. And let's see here, let's distribute the negative. This will be a minus 2 times 2 is 4. And then the negative will distribute and change that to a plus 3. And our denominator is delta x. And let's see what happens now. Now in that numerator, let's look for stuff to cancel. I see some numbers that'll line up nice. Here's a positive 3 and a negative 3. And there's a negative 4 and a positive 4. Oh, beautiful. All those just cancel right out. Look what we're left with. 2 delta x over delta x. 2 delta x over delta x. So we want to try direct substitution again, and here we'd get 0 over 0. But when we do the cancellation, we just get 2, and there's no longer a place to plug the 0 into, so that's our limit. The limit is 2. The exact slope occurring at that point is 2. Now, I didn't point this out at the beginning of the problem. This function is 2x minus 3. It's just a straight line. No matter what point we used, we were going to get a slope of 2. But this is a great simple example just to show you the mechanics of one of these type problems. When they give you the x value right at the beginning, you can just plug that in when you're using that difference quotient. Most of what we're going to be doing in this class is not going to be like example 1. It's going to be more like example 2. See, now here they give us a function and they ask us to find the slope at a couple different points. Now we could do the same method we used here for the first point and then go through it all again for the second point. But to save time, we're just going to find the general derivative. And once we have that general derivative, we can plug in this x value 0 and get the slope here. And we can plug in this -1 and get the slope occurring at that point. So this, again, it's going to be a little different. Here, when we're done, we're going to have a whole new function. So here, we want the limit as delta x is going to head close to 0. And our function is x squared plus 1. So I'm going to do the old empty parenthesis. Here is something squared plus 1 minus grouping symbol, another something squared plus 1. So there's the difference in our difference quotient, f of something minus f of something else. And this all goes over delta x. So now here we're going to plug in x plus delta x. Remember back in the last example we plugged in a 2 plus delta x because they gave us the 2. Here we're going to find again a different function. So this is going to be x plus delta x. And over here we're just going to plug in the x. Now I am going to drop my limit notation because I am going to need a little more room here. We're going to FOIL out this first term. I'm underlining in blue, x plus delta x squared. That's going to be x squared plus 2x delta x plus delta x squared. And it's real easy. Don't forget this plus 1 here. That wants to come along for the ride. And I'm going to switch back to red ink. Here we can just distribute this negative. This will be a minus x squared. Oop, that's a pretty terrible exponent. Let me fix it. There we are. And distribute this negative to make that a minus 1. And this is still all over delta x. I guess I could have squeezed in my limit notation. Well, let's see. Again, we want to try direct substitution. If we tried it immediately, we would have gotten 0 over 0. So now let's do a little simplification with some algebra and see what happens next. Okay, here we got a negative x squared. Ooh, and right at the front we got a positive x squared. Those are going to cancel. We've got a minus 1. Here's a plus 1 to cancel it out. Notice the second use of the function up here. All the stuff I did in red ink canceled out. All right, and now notice what we have left. Let me rewrite it here so it's a little easier to see. Every term we have left has a delta x in it. In the numerator, there's a 2x times delta x, and then there's a plus delta x squared, and our denominator is delta x. If we try direct sub right now, we still will get 0 divided by 0. But we can cancel a delta x. Now there's a couple ways to think about it. The safer way in this numerator, if I put some red brackets around it, we can factor this delta x out front. Oops. We can factor it out front and then cancel it with the delta x downstairs. That would look like this. We factor out the delta x. That would leave a 2x plus. There would still be one of these delta x's left because this was squared. And this is all over delta x, so those would cancel out. So again, that's the safer way to do this. When you're more confident and you can look at a problem like this and say, okay, well, I'm going to cancel this one in the denominator. So this one is first power. It's gone entirely. This squared gets knocked down to first power. And what we're going to be left with, either way, is this 2x plus delta x. Our limit still wants to head to 0, but now it's safe to do so. If we're going to let delta x go to 0, that 0 is going to plug in right here. It's no longer division by 0, so this is just going to turn into a 0, and our answer is 2x. So now let me point out something in the big picture. Our function f of x. This is a position function. If you put in an x value, out pops your y value, and you can plot that in the xy plane. What we found here is a derivative function. And I don't know, have I introduced the notation yet? This will be f prime of x. Our original function was f of x. We denote a derivative. The easiest way is by this prime notation. So f prime of x is 2x. This is also a function. Our original function was a position function. This is a slope function. We put in x values and slopes pop out. Again, the original function was a position function. X values goes in, y values come out. This is a slope function. X values go in and slopes come out. Now, if we think back to the start of this problem, they asked us to find the slope at the point 0, 1. At 0, 1, f prime of 0 would be 2 times 0. Our slope would be 0. Remember, 0 slope would be horizontal. They also asked us at negative 1, 2. At negative 1, 2, f prime of negative 1 would be 2 times negative 1, or negative 2. I'm having too much fun. Let's look at the point 3, 10. On the original function, our shifted parabola, if I plug in a 3, out pops a 10. My slope at that point would be f of 3, or 2 times 3. That slope would be positive 6. Let me bring the graph down so we can look at some stuff on there. So here's our graph. X squared plus 1 is a parabola shifted up. The first point we investigated was at 0, 1. That would be right here. We had a 0 slope, and that is the bottom of our parabola, getting hit by that tangent line. And then we went to negative 1, 2. There's our point at negative 1, 2. And the tangent line's hitting that parabola. We can see the slope is steeply negative, negative 2 to be exact. Now, we would have to go off the graph to see this, but if we went out to 3, we would go way up on that parabola, and our tangent line would be much steeper. Think about it, here's just a basic parabola. As we head up, it's getting steeper and steeper. Our tangent line would be getting very steep pretty quick. So again, big picture, f of x is a position function. X values go in, y values come out, so you can locate your position. Derivative functions are slope functions. X values go in, the same x values go in, and a slope comes out. So the slope at any point, c comma f of c on this graph, they're using c's, I used x's. We had our derivative was 2x here. They're just saying 2c. So at that point 0, 1, the slope is 0. Yeah, we already talked about this. The definition of a tangent line to a curve does not cover the possibility of a vertical tangent line. For those vertical tangent lines, we could use the following definition. Well, it's just going to be heading toward infinity. Think about, here is 0 slope. The slope, as our numbers get more and more positive, bigger and bigger, we get steeper and steeper. We could have a slope of 1 billion. You'd go up 1 billion and over 1. Or we could have a slope of 1 trillion, up 1 trillion and over 1. We would be heading for infinity. Either positive or negative infinity would be valid, because once it goes vertical, it doesn't matter if you come in from either side. Our slopes can be infinite in that way of thinking, I guess. Blah, blah, blah. It goes through, this would be a vertical tangent line to the graph. So here's a function. Here's an example. We have some functions that might curve like this. And to the left of this, we would be steep and getting steeper and steeper and steeper. And there is just one point right in the middle of that graph right there where that tangent line would go vertical. So here it is, the derivative of a function. We've now arrived at a crucial point in our study of calculus. The limit used to define the slope of a tangent line is also used to define one of two fundamental operations of calculus, differentiation. The derivative of function f at point x is, here's our limit definition, that difference quotient, and there's the notation I talked about in that last example. F prime of x is equal to our limit as our delta x approaches 0 of our difference quotient, f of x plus delta x minus f of x over delta x, provided this limit exists. For all x values for which this limit exists, f prime is a function of x. It's a slope function. Be sure you see that the derivative of a function is also a function. This new function gives us the slope of the tangent line at that point, provided the tangent line or the graph has a tangent line at that point. The derivative can also be used to determine the instantaneous rate of change, or simply the rate of change of one variable with respect to another. The process of finding the derivative of a function is called differentiation. A function is differentiable at x when its derivative exists at x, and is differentiable on an open interval from a to b when it's differentiable at every point in that interval. In addition to f prime of x, other notations are used to denote a derivative. So here are the most common. We already talked about this one, f prime at x. Here's another one. If we have y equals f of x, then the derivative we could denote as dy dx. dy means the derivative of y. The dx means with respect to the x variable. So dy dx, it's the same thing as f prime. And because I already wrote this here, let me use this. With this, y equals f of x, we do have f prime is the notation for a derivative. You could also just say y prime. Y prime is also derivative notation. This you see once in a while. Our function is f of x, so if we were going to derive that, we could denote it by putting this d dx in front. Here is my function f of x. We are going to derive with respect to x, d dx of f of x. This last one, of all the calc books I've read, and it's been quite a few, I've never seen that notation widely used, d of x of dx of y. And just that second one here, the book does write out how to say it. The notation dy dx is read as the derivative of y with respect to x, or simply dy dx. So using limit notation, we can write it like this. dy dx is the same thing as our limit as our delta x heads to 0 of our change in y over change in x. That's also our difference quotient, and that's the same thing as f prime. So lots of new notation for us in this class. So take your pick. I encourage you to mix it up a little bit. Don't become too set using one of these notations. If you're taking the AP test, they'll mix it up pretty good. And here we go. Finding a derivative by the limit process. Find the derivative of x cubed plus 2x. Use the definition of a derivative as shown. So here is our definition. F prime is the limit as we approach 0 of our difference quotient. Now, I'm going to skip the limit notation here. I will not have room, especially in the, well, I can use it in the first step, I guess. The limit is delta x goes to 0. So the numerator, I'm going to use my empty parenthesis. Something cubed, oops, let me make that a little bigger. Something cubed plus 2 times that same something. So there's one use of that function. And then we're going to subtract its use again as a quantity. So something cubed, that's a terrible exponent. Let me fix it. Something cubed plus 2 times something. There, it barely fit, but we got it in. All over delta x. And what's going to go in there is x plus delta x in the first use, x plus delta x, x plus delta x. And in that second use, it's just plain old x, because that's our notation here, f of x plus a little bit more minus f of x. Now comes the fun part. This quantity cubed. Do we remember Pascal's triangle and a binomial expansion? Remember, the coefficients for a third power expansion are 1, 3, 3, 1. And since this is a plus, every term will be positive. So my first term is going to be x to the third. And you could think plus delta x to the 0 power, but delta x to the 0 is 1, so we can ignore it. Our next term, and this is a 1x cubed, we'll have a 3 in front. The x is going to go down 1 power to x squared, and here we have a delta x to the first appear. 1, 3, 3 is our next coefficient. X drops a power to x to the first. Delta x increases the power to delta x squared. 1, 3, 3, 1 is our last coefficient, so I'm not even going to write it. X goes down a power, so we could write x to the 0, but that's 1, so we won't. But then we're going to have a delta x to the third. And I did write way too big because, that is just this part here expanded out to the third power, but it looks good. And also, what helped me, especially when we're canceling stuff later, I sometimes put my delta x's in their own sets of parentheses. Just so they sort of stick out. They won't blend into the x's that I write. And that's just something that I do. You don't have to. So I am going to scrunch this up a little bit, because I can do that with this software, because we're just getting started here. We've still got this part. Back up to the difference quotient, back to black ink right here. We have 2 times x plus delta x. We're just going to distribute that 2. So we're going to have a plus 2x plus 2 delta x. So 2 is distributed. Now here we're just going to distribute the negative. So that'll be a minus x cubed and a minus 2x. And I barely have room, but it fits. Again, I do not have my limit notation. That should be out here to the left now. Again, we always want to try direct sub in that 0 as soon as we can. If we did it at the beginning, we would have got 0 divided by 0. But let's see what's going to cancel here algebraically. I did write the second use of the function at the end there in that numerator in red ink. And as usual, you should notice this every time you do one of these, all of those terms should cancel. So let me switch to blue ink. Here is a negative x cubed. That is going to cancel the positive x cubed from the very start of this, so I'll just scribble those out. And the minus 2x, here is a plus 2x. That should always occur. If it doesn't, something went wrong with the algebra. So now I will have room for my limit notation. Notice now everything left in the numerator has a delta x at least to the first power. So this delta x in the denominator, its first power, I'm going to cancel it. This delta x here is first power. I'm going to scribble it out. This delta x squared is now down to first power. This delta x to the third is now going to be down to squared power. And this delta x here was first power, so it gets canceled. So a lot of scribbling here. Let's see what's left. Again, our denominator is entirely gone. So we have a 3x squared is there, 3x squared. We have a 3x delta x, 3x delta x. This delta x got knocked down to a squared, so we still have a delta x squared. And here is a plus 2, plus 2. Since our denominator is gone, it's safe now to do direct substitution. Let that delta x turn into a 0. So this delta x turns into a 0. That zeroes out this whole term. Gone. This will be a 0 squared. It's also gone. So what are we left with? 3x squared plus 2. So coming back up here, they were asking us to find that f prime. F prime of x is 3x squared plus 2. The original function would give us a y value so we could plot our position. If we plug the same x value in here, we'll get the slope that is occurring at that point exactly. Use the derivative to find the slope at a point. Here we want to find that f prime at the function root x. And then it says find the slopes of the function at the point 1, 1 and 4, 2. Discuss the behavior of that function at the origin. Okay, so this one, our function is f of x is root x. I'll underline that there in red. So we're going to find the limits as sometime we're going to send delta x off to 0. We're going to have our function, the root of something, and then we're going to use it again minus the root of something. Remember, the first time we use it, it's going to be x plus a little bit more, but then we're going to subtract the original x. And this is all over delta x. If we try direct substitution, I plug in the delta x is 0. We get root x minus root x upstairs, all divided by 0. It does not look good. So what the heck are we going to do? Think back to when we were doing limits algebraically. We had the factor and divide out technique. Another technique was multiply by the conjugate. So what I'm going to do is just scrunch this up a little bit. And we are going to multiply by the conjugate of the numerator, the root of x plus delta x plus a root of x. And if we're going to multiply the numerator by something, we have to multiply the denominator by the same thing. So in effect, we're multiplying by 1, and we're not changing the problem. So I'm going to come down here, and as we FOIL, we're going to have our first radical times our first radical. That means the radicals will disappear, and we have x plus delta x escapes. And then we have a negative root x times a positive root x. That'll be a minus x. Down in my denominator, I encourage you not to distribute, just like I did back in that other section. So down in our denominator, we're going to have a delta x times that conjugate, root of x plus delta x plus another root of x. So look what happens in our numerator. We have a positive and negative x. Those are going to cancel each other out. Negative x, positive x, gone. And that's a good thing because now we can now cancel with this delta x in the denominator. You know, if you did distribute it, it might be harder to see. But right here, we're just going to cancel. Don't forget that that delta x in the numerator, at the very least, was a placeholder. So there still is going to be a 1 up in a numerator. And down in that denominator, we have our original conjugate, x plus delta x under a root plus another root of x. So we tried direct sub at the beginning. Let's see if direct sub works now. So we let delta x go to 0. So a 0 jumps in for this delta x. That just turns into a 0. And we have 1 over a root of x plus another root of x are 2 roots of x. That is our derivative, f prime. Or we could write it as, since that was f of x, we could write df dx, I guess. That also works. So the original function is the square root. Here is our derivative. The original function gives us a point. This gives us a slope. Now they did ask us to find the slope at a couple points. Blue ink here. What's the slope at 1, 1? At 1, 1, f prime of x, oops, I should write that as f prime of 1, will be 1 over 2 times the root of 1. Root of 1 is 1, so that's just a half. Our slope would be 1/2. What about the point 4, 2? At the point 4, 2, our derivative f prime of 4 would be 1 over 2 times the square root 4. That root of 4 is a 2, so our denominator is 2 times 2, which is 4. Slope is 1/4. And then it says, discuss the behavior at 0, 0. Let's take a look at the graph here, because if we plug in 0, there we go. If I try to plug in 0, we're going to get 1 over 2. Let me even back that. There we go. If we do try it at the origin, at 0, 0, we're going to get 1 over 2 times the root of 0. 2 times 0 is 0, so that would be 1 over 0. Remember, indeterminate form is 0 over 0. So here we have a number in the numerator. And our denominator, at least we were approaching 0. We can't divide by 0. So it looks like here was a vertical tangent line. Now let's think about or look at this graph. Here's the slopes we found. At 1, 1, our slope is a half. At 4, 2, our slope is a fourth. But as we approach the origin, we're sort of moving down this curve. Our graph is getting steeper and steeper. It looks like we were approaching positive infinity. And remember, the graphical idea of a tangent line is we're tangent at a single point. When we get to the end of this square root graph, you know, there is nothing beyond the origin. That's the end of the road. If you want to draw a tangent line here at the origin, I could actually draw infinitely many tangent lines going through there. So there is no one tangent line at that end point. All right, example 5. Find the derivative with respect to t for the function y equals 2 over t. So here they just changed up the variable 2 over t. Y equals 2 over t. So we want the limit as delta t approaches 0. Now here in our numerator, our function is 2 over something. So we're going to have 2 over something minus 2 over something, all over delta t. What goes in the first use of the function? Here will be t plus delta t minus the original t. So direct sub would give us 2 over t minus 2 over t all over 0. 0 divided by 0, not a good thing. So we're going to have to try some algebra. Remember back when we did limits, we had where we would combine fractions. And at some point, we would bring up our denominator and flip and multiply to get rid of that division by 0 opportunity. So it looks like we're going to try something like that here. I can keep my limit notation. I should have room. Delta t will approach 0. So think back to that section on limits. Our denominator here between these, let me switch to blue ink. This denominator between these two is going to be t times t plus a little bit more. And we're not going to distribute there. And then this numerator 2 is going to get multiplied by t, so that's going to be a 2t. Remember here the negative is attached to what comes after it, so that's going to be a negative 2 times quantity, the other denominator, t plus delta t. And this is all over down here. I'll switch back to black ink. Delta t, we could put it over 1 just to remind us that we are going to be bringing that up and flipping it before too long. And we let the algebra flow. This negative 2 we're going to distribute. So that's going to be a negative 2t. Let me write it down here. We have a 2t, and then we distribute negative 2t minus 2 delta t. Our denominator for that part is still t times t plus delta t. And underneath that, let me do a red divider line here. I'm going to move this up. And underneath that is still my delta t over 1. So this comes up. And we still have our overall denominator, delta t over 1. So the algebra, 2t minus 2t, those are going to cancel. We're going to bring this up and flip it so it's 1 over delta t here. On the diagonal, we're going to cancel out those delta t's because there's just that one attached to the -2. It'll cancel with the one underneath this 1, and our division by 0 problem has just disappeared. So in this next step, we can let our delta t go to 0. Let's see what we're left with. -2 is the only thing left in the numerator, and then we have t times t plus that delta t. So delta t turns into a 0. That zeroes out. So t plus 0 is t. So downstairs we have t times t. -2 over t squared is our derivative. Let's get some notation attached to that. Our original function here was y equals 2 over t. So we could write y prime equals, or, our function was y and we derived y, dy, we derived it with respect to this variable, dt. So we could say dy dt is -2 over t squared, or we could say y prime, -2 over t squared. And what it looks like there's a graph to go with that. Ah, there it is. So there's our function 2 over. Did they ask us to find a tangent? Oh, they did. I almost ended the problem a little bit early. Find the equation of the tangent line to the graph at 1, 2. Notice they're not just asking us for the slope. And our derivative, let's use y prime, that was -2 over t squared. Let's think back to Algebra 1, Algebra 2. We want to write the equation of a line. We need two things. We either need 2 points, a point and a point, so we can find the slope between them, or we need the slope and 1 point. Now what we found, well, they gave us a point. Here's the point we want to be tangent at, 1, 2. So we want a point, and they gave us 1, 2. We now need the slope, and we found the derivative. Remember, the derivative will give us the slope. So the slope occurring at the point 1, 2, we plug the x value in, or in this case, it's the t value. That will be over 1 squared. -2 over 1 squared is -2. So slope is -2. Our point is 1, 2. Y2 minus y1, mx2 minus x1. Here is, well, we could write this. Y minus y1 equals mx minus x1. That'll be a little easier to use. So they gave us a point and a slope, and here is point-slope equation of a line. Our slope is -2, so our m becomes a -2. We have y minus something. Over here in the parenthesis, x minus something. We plug in our x's and y's. X is 1, y is 2. So y minus 2 equals -2x minus 1. Well, we're going to get the y value alone. Here we're going to distribute the -2, so that will be a minus 2x. When we distribute here, that will be a plus 2. But then we're going to add 2 more. So 2 plus 2 is 4. -2x plus 4 is our tangent line equation. That's a real common in calc classes and on calculus tests to find not just the point of tangency, but the equation of the tangent line at that point. So let's look back to this calculator graph they have for us. Original function would be here, 2 over t, that downward sloping in the first quadrant. Our point was a 1, 2, and we could actually graph the tangent line in the y editor down on the next line, -2 plus 4, and then we'd have our tangent line appear right on that graph. Beautiful, beautiful mathematics. Now, there is a relationship between being differentiable and being continuous. Here they have an alternate limit form of a derivative shown below. It's useful to investigate the relationship between being differentiable and being continuous. So the derivative of function f at point C, f prime at C, the limit as x approaches C, f of x minus f of c over x minus c. This is still just, regular old slope, y2 minus y1 over x2 minus x1. Here they're just using x's and c's. And if we do try direct sub, our limit as x approaches c, we would plug in c for all the x's. So it'd be f of c minus f of c over c minus c. So we would still have that 0 divided by 0 problem, but this is just an alternate form of that derivative, provided that that limit does exist. And then note that the existence of a limit in this alternate form would require that the one-sided limits also exist. So here we would be approaching c from the left. Here we would be approaching c from the right. These would have to exist and also be equal to each other. These one-sided limits, we can call them just like a limit from the left to right, derivatives from the left and the right. And then it follows that f is differentiable on some closed interval between a and b, but it's differentiable at every point inside that interval. And when it is when the derivative from the right at the left endpoint, a, and the derivative from the left at the other endpoint both exist. When a function is not continuous at some point, it's also not going to be differentiable at that point. For instance, the greatest integer function, that step of x, it's not continuous at the origin. So it would not be differentiable at that x value. We can also see here, here's our step of x function. If we approach from one side, our limit would be infinity. Coming from the other side, it would be 0. So they're not the same, they're not equal, so we would not be differentiable at that point. Now here, a graph with a sharp turn. For this, we're just going to use that alternate form they showed us there. And let me do this. The limit as x approaches 2 from the right side. So, we're going to come in from the left, from the minus, from the left side. So we're going to do f of x minus f of 2. That's supposed to be a 2. F of 2, f of 2 over x minus 2. So I just use this alternate form. Where did that go? No, I lost it. I dragged that slide up. Nope. There it is. F of x minus f of c over x minus c. That's all we've got here. F of x over f of 2 over x minus 2. Now let's actually plug in the function that they gave us. This f of x, let me switch to red ink. This f of x is just the absolute of x minus 2. And that's going to be minus f of 2. Well, what happens if we put 2 into that function? We get the absolute of 2 minus 2, or the absolute of 0, or just 0. Down in our denominator, we have x minus 2. So that minus 0, I can just sort of erase that off. Let's see here. We're approaching from the left side. We're approaching from the left. Our numerator is, let's pick a number a little bit to the left of 2. Here's 2. If we're approaching from the left, think 1.9. So in the bars, I would have 1.9 minus 2, and the bars would force it to be positive. Downstairs, 1.9 minus 2 would be the same value, but it would be negative. Because remember, if we look at this, this is something divided by itself. It's always going to equal 1. In this case, our numerator is positive, our denominator is negative, so this is negative 1. Our derivative from the left is negative 1. Negative 1. And let me even write deriv from left. Deriv from left. If we come in from the other side, as x approaches 2 from the right, it's going to look exactly the same. We are going to have the absolute of x minus 2, that's our function f of x, minus f of 2 will be minus 0, just like we saw from the other side. Downstairs is x minus 2. So it looks the same, but now we're coming in from the right of 2, or numbers a little bit bigger than 2. So if we imagine 2.1, our numerator is going to be a positive 0.1, and our denominator, 2.1 minus 2, will also be positive. So this is positive 1, our derivative from the right. Deriv from right. Derivative from the left is this. Derivative from the right is something else. We are not differentiable at that point. Here's what our graph would look like. Remember, derivatives tell us about slope. As we come in from the left, our slope was negative 1. When we got to point 2, on the right of that number, our slope is positive 1. So our derivative from the left and the right were different. And we can also note here in the graph, the graph of this function has a sharp point or a cusp. Remember, derivatives show us slopes of tangent lines. I could draw a bunch of different tangent lines at that sharp point. So if our graph is sharp like that, we will not have a derivative at that point. And we saw it here backed up with some algebra. Example 7, x to the third power, or the cube root of x. Cube root of x. It is going to look something like this. This function is continuous at 0. When I draw this graph, I don't have to lift my paper from the pencil. I can draw that graph as a continuous function. But let's see what happens with the limit as we come in at 0 using this same alternate form. Remember, this is f of x minus, in this case, f of 0 over x minus 0. And I have plenty of room. I should have put my limit notation in there. The limit as x goes to 0 of this. My function is x to the third, or the cube root of x. So this is going to be the cube root of x, or x to the third, minus f of 0. The cube root of 0 is 0, so that would just be minus 0. And we don't even need to write it in there. Down in the denominator is an x. So x to the third over x, if I tried to rec sub, I still get 0 over 0. But remember our properties of exponents from Algebra 1. Our numerator is x to the third. Our denominator is same base, different exponent. So we can use our properties of exponents to rewrite this as we could subtract. 1/3 minus 1 would be negative 2/3. And if we move it to the denominator, we can make it positive again. So this becomes, we're approaching 0, 1 over x to the 2/3, or the cube root of x squared. Now, if we tried to rec sub, we are going to be dividing by 0. But in this case, it's not 0 divided by 0. It's not indeterminate form. So for this one, let's see. Let me rewrite it as, this would be the third root of x squared. Now we could approach 0 from the left, and we can approach 0 from the right to see if they're different. But notice we're letting x approach a number. Here x is squared. So under this radical, it doesn't matter if we're positive or negative. We're going to square it. This is going to be positive. We're going to cube root a positive. So this is going to be a positive denominator. positive numerator, positive denominator. As we approach 0, this is heading for positive infinity, or a vertical tangent line. Remember, this would be a vertical tangent line, and we would say f is not differentiable at this point. F of x not differentiable at 0, 0. We would have an infinite slope or a vertical tangent line to our graph. Here's our cubic function. And as we're coming in from the left here, here our slope is positive, and then it gets steeper and steeper and steeper. And the closer we get to the origin, the steeper it gets. At the origin, for one moment, it's completely vertical. And then we're over here, and our slope is decreasing. It's positive, but it's back to going downhill. Or the slope is decreasing. We're not going downhill, but the slope is getting less and less positive. So this brings us to a theorem, Theorem 2.1. I believe this is the last slide. Yes. Theorem 2.1, differentiability implies continuity. The reverse of that is not true. If our function is differentiable, then it must be continuous at that point. If it's differentiable, then it's continuous. If you try to rewrite that, in the alternate form, if it's continuous, then it has to be differentiable. That's not true. We just saw two examples of that. I can draw the absolute value of x graph, and it's continuous. Here's a xy axis. Here's my absolute value of x graph. It's got this sharp point. I can draw the graph as a continuous function without lifting my pencil off the paper, but it is not differentiable at that sharp point. So this is only true forward, not backwards. If it's differentiable, then it has to be continuous. That sounds like it would make a great test question, maybe true and false, or I don't know. That's something to think about. So that's the end of this video. I hope you had fun.